previous lecture, we started our discussion in the topic of differential calculus for functions of several variables. In particular, we started our discussion with the notion of limit and then continuity for functions of several variables. We have also got to know two special kinds of continuity. Those are uniform continuity and Lipschitz continuity. We have found that Lipschitz continuity and uniform continuity identify two special kinds of functions that do not allow a sudden rapid change of the function value. In this lecture, we shall start our discussion with the notion of partial derivative that identifies instantaneous rate of change of the function value at a given point along the axis of the argument of the function. Now, after identifying these partial derivatives, we shall also get to know the notion of directional derivative that identifies instantaneous rate of change of the function value at a particular point along a given specific direction. After this directional derivative, we will also get to know the notion of differentiability for functions of several variables. That geometrically ensures that there exists a tangent plane on the surface of the given function of several variables. Neatly, in this lecture, we will describe three notions for functions of several variables. Those are partial derivative, directional derivative, and the notion of differentiability. For a function of one variable, we all know the definition of the derivative of the function at a given point, say C, in the interior of the domain of the definition of the function, which is defined by the existence of the limit h tends to 0 of the quotient f c plus h minus f c divided by h. If for a function of one variable this limit exists, then we call the limit value as the derivative of the function f at the point c, and this derivative value is usually denoted by f dash c or df dx at the point x is equal to c, or simply by df at the point c. And we all know this limit value signifies the slope of the tangent on the graph of y is equals to fx at the point c. For a function of two or more variables, the notion of derivative is defined in the following manner. Let's suppose we are given a function of several variables, say f of x1, x2 till the nth variable xn, and let's suppose we wanted to identify derivative value of this function f at a point, say C, in the interior of the domain of definition of the function f. Let's suppose the point C has coordinates c1, c2 till cn. In calculating derivative of the function f with respect to one of the variables, say xj, what we do is we hold all the variables xis at the value ci, except keeping xj as a variable. The function f reduces to a function of only one variable xj. Let's suppose this function of xj is the function phi, which is a function of only one variable. Now we compute the usual derivative of function of one variable for the function phi at xj is equal to cj. The derivative value of the function phi at xj is equal to cj is called partial derivative of the function f with respect to the variable xj. Because during all this process we see that we kept all variables fixed at some constant values, and we are only allowing the variable xj to vary. That means we are partially allowing just one variable xj to vary and then computing the instantaneous rate of change of the function at xj is equal to cj. Thus, we call the derivative value of phi at Cj as the partial derivative of the function f with respect to the variable xj. Now we see that this derivative value of phi at Cj is given by limit hj tends to 0 phi cj plus hj minus phi cj divided by hj, which in terms of the function f is limit hj tends to 0 f of c1 c2 till cj minus 1 tj plus hj tj plus 1 till cn minus f of c divided by hj. Note that this entire expression or the coordinates inside this function f can be written in the vector form as c plus hj times ej, where ej is the jth unit vector in the standard basis of Rn. That is, ej has n many components, all zeros except 1 at the jth position. Hence, in turn, this limit can be expressed as limit t tends to 0 f of t plus tej minus f of c divided by t. If this limit exists, then that limit value is called the partial derivative of the function f at the point c with respect to the variable xj. So we write here that if limit t tends to 0, 1 upon t into f of c plus tej minus f of c exists, then the limit value is called partial derivative of the function f at the point c with respect to the jth variable xj, and we denote this limit value commonly by del f del xj at the point x is equal to c, or by f subscripted xj at the point c, or by capital D subscripted j of the function f at the point c. Here we note that partial derivative of the function f at c with respect to xj is nothing but the usual derivative of the function phi, which is a function of one variable, and hence similar to derivative value as the slope of the tangent, we can also identify a geometrical interpretation of partial derivative as follows. I will give the geometrical interpretation for a function of two variables, and for functions of more than two variables the interpretation will be similar. Let's suppose we are given a function of two variables x1 and x2, and let us try to identify a geometrical interpretation of the partial derivative of f with respect to x1 at a point say c1 c2. While calculating this partial derivative with respect to x1, we eventually calculate the derivative of the function f x1 c2. That means we are holding up x2 at the value c2, then we get a function of one variable x1, and we compute the derivative of this function of one variable at x1 is equal to c1. We notice that this function, say phi x1, is obtained by taking intersection of z equals to f x1 x2 and x2 is equal to c2. Geometrically, z is equal to f x1 x2 is a surface in the 3D space. Let's suppose the surface of z is equal to f x1 x2 is this one, and the location of the point c1 c2 is somewhere over here. Say, let's suppose this is the vertical plane, x2 is equal to c2. Therefore, the graph of z is equal to phi x1 is the curve given by the intersection of this vertical plane with the surface of z is equals to f x1 x2, which is this curve say which lies entirely on the surface of z is equal to f x1 x2. So we got the graph of the function z is equal to pi x1, which is a curve entirely lying on the plane x2 is equal to c2. We notice that on x2 is equal to c2, the variable x1 is getting varied, but x2 is kept fixed at the constant value c2. At this point c1, c2, the value of the variable x1 is equal to c1. Now at this point x1 equals to c1, we find out corresponding point in the curve of z is equals to phi x1 and find out the slope of the tangent to the curve z equals to phi x1 at the point x1 is equal to c1, and the slope of this tangent line at the point c1 c2 is the partial derivative value of the function f with respect to x1 at the point c1 c2. Similarly, for the partial derivative of the function f with respect to the variable x2 at the point c1, c2 can be identified by taking slope of the tangent on the curve of intersection of z is equal to f x1 x2 and x1 is equal to c1. I am keeping this as a home task that you please draw a similar figure and try to figure out the intersection curve of z equals to f x1 x2 and x1 equals to c1, then try to find the tangent line at the point c1 c2. Now here we notice that while calculating the partial derivative with respect to x1, we are eventually taking derivative value of this intersection curve z equals to phi x1, and while calculating the derivative value of this function phi of one variable x1, we focus our attention on this line x2 is equal to c2, then we vary ourselves in the neighboring point of c1 c2, and then we calculate the instantaneous rate of change of the function value around the point c1 c2. Now when we are on this line x2 is equal to c2, we see that we are only moving along the direction of x1 axis, that is along the direction of the unit vector 1 0, or with our usual notation along the vector u1. So effectively, while calculating the partial derivative of the function f with respect to x1, the movement of the variable values x1 x2 are only along the direction of x1 axis, and hence this partial derivative effectively finds instantaneous rate of change of the function values at the point c1 c2 along the direction of the x1 axis. Similarly, the partial derivative of f with respect to x2 at c1 c2 is instantaneous rate of change of the function values at the point c1 c2 along the direction of x2 axis. And in general, partial derivative of a function f with respect to its jth variable is instantaneous rate of change of function values or f values at the point C along the direction of jth unit vector in the standard basis of Rn. Now after calculating partial derivative of the function f with respect to the jth variable at different points C in the domain of the definition of the function f, we will get a function of the variable vector x. Now as this is again a function of several variables, we can go for calculating partial derivatives again for this function, and the partial derivatives of this function will then give us higher order derivatives, or in specific second order partial derivatives of the function f. So second order partial derivatives are partial derivatives of the partial derivative functions f(x)j's. Denotations of higher order partial derivatives are as follows, that let's suppose we have calculated partial derivative of the function f with respect to the variable, say the jth variable, and then we go for calculating partial derivative of this function with respect to the variable, say xi. This partial derivative is called a second order partial derivative of the function f. This is commonly denoted by del 2 del xi del xj of the function f. A short notation of this partial derivative is f subscripted by xi xj, because the subscripted notation fxj denotes this partial derivative, and then we take partial derivative of this function with respect to x1, so we use this subscripted denotation fxi xj to denote this second order partial derivative. Now varying ij's inside the all possible index values 1 to till n, we will get all second order partial derivatives of the function f. Here you notice that in calculating these second order partial derivatives, we take at first the partial derivative of the function f with respect to xj and then with respect to xi. If we consider both the variables xj and xi identical, that means say we are taking del xi of del xi of the function f, then we use the notation del 2f del xi2 to denote the second order partial derivative, which is partial derivative of the function f with respect to the variable xi twice. When xi and xj are two different variables, that means when I is not equal to j, we call this second order partial derivative, that is f xi xj, as second order mixed partial derivative, as if we are mixing up the variables xi and xj while taking the second order partial derivative, that is with respect to the variable xj first and then with respect to some other variable xi. Now taking partial derivative of these second order partial derivative functions, we will get third order partial derivatives of the function f, and to calculate fourth order partial derivatives of the function f, you consider four variables of the function and then keep taking partial derivatives with respect to the four variables one after another. And for fifth order partial derivatives, you choose five variables and so on. For third order partial derivatives, we use the notation del q del xi del xj del xk of the function f, which is del xi of del 2f del xj del xk. Now here I would like to ask you a question, that let's suppose we are going for calculating second order mixed partial derivatives of a function of several variables. In calculating second order mixed partial derivatives, we obviously have to consider two variables, say xi and xj, that are different from each other. After choosing these xi and xj out of these x1, x2 till xn, which are the variables of the function f, let us suppose we have calculated partial derivative of the function f with respect to the variable xj first and then with respect to the variable xi. Then we go for calculating the second order mixed partial derivative by interchanging the order of xj and xi. That is, we calculate partial derivative of f with respect to xi first and then with respect to the variable xj. Now my question is, at a given point say C, are these two mixed partial derivatives equal? That means the question is, can we always interchange the order of the variables xi and xj while taking the higher order partial derivatives, or in particular second order mixed partial derivatives? That is precisely, is this equality valid for any given function f? Answer to this question is negative. For instance, we consider the point C to be the origin in the R2 plane and the function defined on the R2 plane is given by x1 into x2 times x1 square minus x2 square divided by x1 square plus x2 square, when this denominator is not 0, that is the point x1 x2 is not the origin of R2 plane and the function value is 0 at the origin of the R2 plane. For this function, if we go for calculating the second order mixed partial derivatives, then we notice that we need to calculate if x1 x2 at origin and also if x2 x1 at origin. To calculate f x1 x2 at origin, we need to calculate del x1 of del f del x2 at origin, which in turn is identified by calculating the limit h1 tends to 0 of f x2 h10 minus f x200 divided by h1. So to calculate these mixed second order partial derivatives, we need to calculate this limit. To calculate this limit, we need to have this numerator expression. In calculating this expression in the numerator, we need to calculate fx2 at h10 and fx2 at 00. Notice that this fx2 at h10 is identified by calculating the limit h2 tends to 0 if h1 h2 minus if h10 divided by h2. Let us calculate what is this limit value. We find that h1 is the value of this limit and hence if x2 h10 is equal to h1. Now we go for calculating if x2 at 00, which is given by limit h2 tends to 0 if 0h2 minus f 00 divided by h2, which is equal to 0, and therefore if x2 at 00 is equal to 0. Hence, this limit pertaining to the calculation of f x1 x2 at 00 is given by limit h1 tends to 0 of h1 minus 0 divided by h1, which is equal to 1, and hence if x1 x2 at 00 is equal to 1. Now I put a home task here that you please verify that fx2 x1 at 00 is equal to minus 1, and hence the second order mixed partial derivatives of the function f are not equal, at the point 0, 0. A question may come here that can we have some mathematical condition on the function f satisfying which these mixed partial derivatives will be equal, so that while calculating the mixed partial derivatives we do not need to bother about the order of taking the partial derivatives with respect to x1 first and then x2, or with respect to x2 first and then x1. The answer to this question is affirmative today, but you know the result on equality of mixed second order partial derivatives is a long history. During 18th and 19th century, several mathematicians including Euler, Bernoulli, Clairaut, Lagrange, Cauchy, all of them attempted to find conditions under which equality of mixed partial derivatives can be realized. But all attempts till 1873 were failed, and in the year of 1873 a famous German mathematician Karl Hermann Schwarz succeeded in giving a mathematical condition and its first rigorous proof for the equality of mixed partial derivative, which states that if two second order mixed partial derivatives, say fxi, xj and fxj xi, are continuous in some neighborhood of a point C, which is an interior point of the domain of definition of the function f, which is a function of n variables, then the mixed second order partial derivatives of the function f are equal at the point C. For a proof of this result for a function of two variables, you may please visit the proof of the theorem 1 on page 100 of the book entitled Advanced Differential Calculus of Several Variables by one of my most revered teacher who taught me function of several variables, Professor Subir Kumar Mukherjee. Now, using the second order partial derivatives of a function of several variables, we will define a very special matrix which is called the Hessian matrix, which will be used quite often during the entire course to check convexity of a given function of several variables or to check optimality of a given point for a function of several variables. In defining the Hessian matrix of a function at a point C, let us suppose all second order partial derivatives of the function f exist at the point C. Then the matrix of order n by n having the ijth entry as the second order partial derivative of the function f with respect to xi and xj at the point C is called the Hessian matrix of the function f at C and denoted by H subscripted f at the point C, which explicitly is the matrix. These elements in the first row, these elements in the second row, and the nth row contains these elements, where all these second order partial derivatives are computed at the point x is equal to C. This name Hessian on this Hessian matrix is named after a German mathematician Ludwig Otto Hesse, who is possibly the developer of this matrix for a function of several variables. Notice that if we consider all the second order mixed partial derivatives of the function f are continuous in some neighborhood of the point C, then this Hessian matrix is a symmetric matrix. This is due to the Sauer's theorem on equality of mixed partial derivatives that we have stated over here. As a note, we write it here that if second order mixed partial derivatives of the function f are all continuous in some neighborhood of the point C, then the Hessian matrix of the function f at C is a symmetric matrix. Because under this assumption of continuity of second order mixed partial derivatives, we have this is equal to this element is equal to this element, and the ijth element is equal to the jith element, thereby making this Hessian matrix a symmetric matrix. Now again we turn our attention on the first order partial derivatives of f, and let me ask you a question that let's suppose we are given a function of several variables, say the function f of n variables, and suppose that the function f has first order partial derivatives with respect to all the variables x1, x2, x3 till xn at a point C in the domain of definition of the function f. Given this, can we assure that the function f is continuous at the point C? The answer to this question is surprisingly negative. I mentioned surprisingly because so far from our knowledge on differential calculus for functions of one variable, we all know if a function f has a derivative value at a point C, then the function f must be continuous at the point C. But for functions of several variables, existence of all the partial derivatives with respect to the variables of the function f at a given point C may not necessarily imply that the function f is continuous at the point C. For example, we consider the function f a function of two variables whose expression is given by x1 x2 square divided by x1 square plus x2 to the power 4, when x1 is not equal to 0 and it is equal to 0 when x1 is equal to 0, and take up the point C as the origin of the R2 plane, then you please verify that both the first order partial derivatives if x1 and fx2 exist at the point 0, 0, and they are both equal to 0. However, we have seen in the previous lecture that this function is not continuous at origin. You please complete your class note by writing why this function f is not continuous at the point 0, 0. So this example shows that existence of partial derivatives with respect to all the variables of a function may not assure the continuity of the function. To find a reason behind not continuous at a point, even if the partial derivatives are all existing, you may think that while calculating the partial derivatives, we are just calculating instantaneous rate of change of the function only along the direction of the axis, and thus the function and its change is not analyzed along every possible direction emanated from the given point C, and maybe due to this not checking out rate of change of the function along every possible direction emanated from C, the function f is appearing to be discontinuous. By all this, I mean to say the following. Let me consider just a function of two variables, say a function of x1 and x2, and suppose del f del x1 at C and del f del x2 at C both are existing, and suppose the coordinates of this point C are C1 and C2. Now you notice that while calculating these two partial derivatives, we are actually analyzing instantaneous rate of change of the function f along the direction of x1 axis and instantaneous rate of change of the function along x2 axis. So existence of these two partial derivatives are effectively informing us there is a finite and definite instantaneous rate of change of the function along this direction and along this direction. However, notice that there are many other directions. Those are emanated from the point C1, C2, but we are not analyzing instantaneous rate of change of the function value along those directions, and maybe due to this reason existence of just these two partial derivatives is not implying the continuity of the function. Let us then go for finding instantaneous rate of change of the function value along a given direction emanated from the point C, but that direction is not necessarily the directions along the variable axis. Let us suppose d hat be a given unit vector emanated from the point C, and we wanted to evaluate instantaneous rate of change of the function f along the direction d hat at the point C. To find this instantaneous rate of change, let us consider any point, say Q, along this ray, and suppose this initial point is the point P. Now when we move from the point P to Q, the function value gets changed from Fp to Fq, and therefore due to the movement from the point P to Q, the function value has been changed by the quantity Fq minus Fp. This function value change Fq minus Fp is due to the movement from the point P to Q, that is due to the movement of the distance from P to Q, and therefore per unit movement along the direction d hat from the point P, the function value has got changed by the amount of Fq minus Fp divided by the length of the line segment PQ. Now if we wanted to calculate instantaneous rate of change of the function value at the point P, we consider the point Q to be closer and much closer, and ultimately when Q approaches to P, we get instantaneous rate of change of the function value along the direction d hat at the point P. Notice that this limit can also be presented as follows. The position vector of the point P is assumed to be given by the coordinates of the point C. If this distance from P to Q is equal to say t, then the position vector of Q is given by C plus T d hat, and hence this limit is given by limit t tends to 0 if C plus T d hat minus Fc divided by t. If this limit exists, then we call this limit as directional derivative of the function f at the point C along the direction d hat. We commonly denote this limit value when it exists by the notation f dash at the point C along the direction d hat. Here I must put a very special note that this direction d hat is a unit vector. If d hat is not an unit vector, then we see that the length of the line segment PQ is given by T times norm of D hat, and accordingly here in the denominator we need to take T times norm D hat. In order to avoid writing every time in the denominator this norm of d hat at the very beginning of the calculation of directional derivative, better we consider d hat to be a unit vector and then go for simply calculating limit of this expression to find the directional derivative. So as a note here, I mention that d hat is a unit vector. I also would like to mention a very special note that in several books of optimization theory, you will find that the definition of directional derivative is given with taking limit t tends to 0 plus. By that, we are effectively calculating one-sided directional derivative, and you know there is a reason behind taking t tends to 0 plus in any of the optimization theory book, that for any given convex function of several variables, this one-sided directional derivative exists for any given direction d hat. However, in this entire course, as and when we will refer directional derivative, by that we will mean this limit definition, and this limit definition will be referred as one-sided or the right-sided directional derivative of the function f at the point C along the direction d hat. Having defined this notion of directional derivative, let us try to figure out a geometrical interpretation of directional derivative. In the geometrical interpretation of directional derivative, let me consider a function of two variables, say f x1 x2, and suppose we are trying to identify a geometrical interpretation of the directional derivative of this function f at the point say c1 c2 along the direction d hat, which is given by the coordinate d1 d2, which is simply the vector d1i plus d2j, where I and j are unit vectors along the directions of the x1 axis and x2 axis. In the 3D space, the space of the variable axis, the axis of the variables x1, x2, and the axis of function value, let's suppose the surface of the function f x1, x2 is this one, and suppose the location of the point C1, C2 in the x1, x2 plane is somewhere over here, and suppose the direction of d hat is this direction. Now while calculating the directional derivative of the function along this direction d hat, we confine the variable vectors x1, x2 to take points only on this ray emanated from the point C1, C2, and on this ray we are actually focusing ourselves to fix our attention on the vertical plane passing through the point C1, C2 and containing this particular line. Now notice that the values of the function f at the points on this line are actually values of the function given by the intersection of this vertical plane and the surface of z equals to f x1 x2. Let's suppose the intersecting curve of this vertical plane and the surface of the function f is this one. Now the directional derivative at the point c1 c2 of the function f along this direction d hat is instantaneous rate of change of the function values of this function at the point C1, C2, which identifies the slope of the tangent to this red curve at this point that is at the point C1, C2. Notice here that this tangent and as well as this red curve are entirely lying in this vertical plane containing the point C1, C2 and passing through the line of the direction d hat emanated from the point C1, C2. After having this geometrical interpretation, let us consider an example to calculate the directional derivative at a given point. Let us consider the function that we took up over here while checking existence of partial derivatives is implying the continuity of the function or not. So we consider the function f x1 x2 given by x1 x2 square divided by x1 square plus x2 to the power 4 when x1 is not equal to 0 and 0 when x1 is equal to 0. For this function, let us try to identify the directional derivative of this function at the origin of the R2 plane along any given unit direction. Let's suppose the coordinates d1 and d2. To identify this directional derivative, we go for calculating the limit t tends to 0 1 upon t times the expression f of c plus t d hat. Here the point c is the origin, so this origin plus t d hat is nothing but f of t d hat minus f at origin, which is limit t tends to 0 d1 d2 square divided by d1 square plus t square d2 to the power 4, which in turn gives us d2 square by d1 when d1 is not 0 and 0 when d1 is equal to 0. And therefore this function f has directional derivative at origin along every possible direction d hat emanated from the point the origin. But we have seen that this function is still discontinuous at the point 0, 0, and therefore existence of directional derivative along every possible direction emanated from the point C does not necessarily imply the continuity of the function. We put this observation as a note that existence of directional derivative along any given direction d hat at a point C does not necessarily imply continuity of the function at the point C. Therefore, neither the existence of all partial derivatives nor the existence of all directional derivatives imply continuity of the function f. Therefore, the notions of partial derivatives or directional derivatives for functions of several variables are somewhat unsatisfactory generalization of the usual derivative for functions of one variable. Because the existence of partial derivatives or directional derivatives do not imply the continuity of the function. Next, we shall consider to relook at the limit definition of derivative or differentiability for a function of one variable in some other way, so that a generalization of that other way or other viewpoint will imply the continuity of the function. This other way or the other notion is the notion of differentiability. For a function of one variable, there is no distinction between the notion of differentiability and existence of a derivative. But derivative is always related with measuring instantaneous rate of change of the function value, but differentiability is related with existence of tangent on the graph of the function at the point x is equal to c. We recall that for a function of one variable, say f, we call it is differentiable or having a derivative at the point c if the limit h tends to 0, f of c plus h minus fc divided by h exists, and let us suppose this limit value when it exists is equal to some number, say capital L, which can be equivalently said that the function f is differentiable at the point c if there exists a finite and definite number capital L such that limit h tends to 0, 1 over h of f of c plus h minus fc minus lh is equal to 0. Now denoting this entire expression in this first bracket by some function alpha, say, which is a function of h, we notice that the differentiability of the function f is differentiable at the point c if there exists a number capital L such that f of c plus h is equal to fc plus L into h plus alpha h, where limit h tends to 0 of the function alpha h over h is equal to 0, which can be equivalently written as there exists an L such that the function fx can be written as fc plus L times x minus c plus alpha at x minus c, where limit x tends to c alpha at x minus c over x minus c is equal to 0. Now you here notice that this function y is equal to fc plus this L, which we usually denote by f dash c times x minus c. This entire expression y equals to this expression is nothing but the equation of the tangent at the point c on the graph of the function y is equal to fx, and we see that this expression capital L times x minus c or this function L times h is a linear function of the variable h, and hence a function f of one variable is having a derivative or is differentiable at the point c if there exists a linear map or a unique tangent on the graph of the function y equals to fx at the point x equals to c. We take up this observation of having a tangent or existence of a linear map to define the notion of differentiability for a function of two or more variables. We call a function of several variables, say f of n variables, differentiable at a point c if there exists a linear map, say capital L of n variables such that f of c plus h is equal to fc plus L of h plus alpha h, where alpha h is such a function that limit h tends to 0, alpha h divided by norm of h is equal to. Notice that this equation is analogous to this equation for a function of one variable. Now from this definition of differentiability of a function of several variables, it is immediate that differentiability of a function of n variables at a point c implies continuity of the function f at c, because simply in this equation you take limit h tends to 0 on both the sides, you will get limit h tends to 0 f of c plus h is equals to fc, and hence the function f is continuous at the point c. Now let us try to identify what could be a possible expression of this linear function capital L when the function f is a differentiable function at the point C. As capital L is a linear function, we notice that L of the vector h can be expressed as L of h1 e1 plus h2 e2 plus so on till hn en, where h1 h2 till hn are the components of h, and these e1 e2 till en are the unit vectors in the standard basis of the Euclidean space Rn. That means the jth element in this standard basis Ej is the vector whose all components are zeros except one at the jth component. Now as the function capital L is a linear function, we have this expression identical to h1 times L at E1 plus H2 times L at E2 plus so on Hn times L of En. Now plugging this expression in this equation, we get that now in this equality we take all His is equal to 0 except the jth index, then we will get f of c plus aj into the vector ej minus fc is equal to aj l of ej plus alpha of all zeros except aj at the jth place. Now divide on both the sides by aj when aj is not equal to 0, and then you take limit as aj tends to 0. You will find that this limit value is equal to L of Ej, and therefore the limit in this left hand side expression exists and equals to L Ej. But what is this limit on this left hand side? This limit on the left hand side is nothing but the partial derivative of the function f with respect to the jth variable xj at the point C, and therefore we get that if a function f is differentiable, then the function is not only continuous at C but also all the partial derivatives of the function with respect to all of its variables exist and given by this equation for every j is equal to 1 to till n. Hence, ultimately we get that the expression of the linear function LH as summation of j is equal to 1 to n of the partial derivative of the function with respect to the jth variable xj at C times the scalar hj. Now here I would like to mention a definition called gradient or the gradient vector of a function of several variables at a point C. The gradient vector of a function of several variables at a point C is a vector in Rn that has components fx1 as the first component, fx2 at C as the second component, and so on, fxn at C as the nth component. We denote this vector by nabla f at C and call it as the gradient vector of the function f at the point C. We can find that for a differentiable function, say f, the gradient vector of the function f at any point C in Rn is perpendicular to the level curve or level surface of the function f that contains the point. By this statement we mean that if we are considering a function of two variables, say x1 and x2, and suppose this curve in the R2 plane is the level curve of the function f that contains the point C. That means if we denote mu to be the function's value at the point C, then this curve is the mu level curve of the function f. That is, L mu is the collection of all points x in Rn such that fx is equal to mu. This result states that the gradient vector of f at C, that is this vector having two components del f del x1 del f del x2, if we are considering a function of two variables at the point x is equal to C, this vector in this x1 x2 plane, if placed at the point C, then that grad f is perpendicular to this level curve. That means this grad f is perpendicular to the tangent at the point C on this level curve L mu. I'll prove this result for a function of two variables. By increasing number of variables, you will get the general proof for functions of n variables. In order to prove this result, we need at first a presentation of the direction of tangent on a curve of points in the R2 plane. Note that any curve in the R2 plane or any curve in the Rn space can be parametrically written with the help of just one single parameter, that this L mu can be presented by the collections of position vectors Rt given by x1 ti plus x2 tj, where I hat and j hat are unit vectors along the directions of x1 axis and x2 axis respectively. Now we see that for a curve in the R2 plane, say this curve, which is given by the position vectors Rt as x1 ti plus x2 tj, and let us suppose we are trying to identify the direction of tangent at this point on this curve RT. To find the direction of tangent at this point P, what we do is we slightly alter the parameter value t to t plus delta t. Accordingly, we will get a point on this curve and calculate the position vector at the parameter value t plus delta t. Let's suppose the position vector of this rt plus delta t is this point, say q. Now we consider this chord on the curve pq. Notice that 1 by delta t times this vector is the direction of the vector pq when delta t is very small, and in the limiting case for delta t tends to 0 of this expression gives us the tangent's direction on the curve of RT at the point P, and this limit is equal to x1 dash t times I hat plus x2 dash t times j hat, which is also denoted by in the vectorial form r dash t. So this r dash t identifies the direction of tangent at the point P on the curve given by the position vectors RTs. Now we come back to relating gradient vector in the level curve of the function f. Here we took up a parametric representation of the level curve L mu. Now on this level curve, we notice that the function f has value mu. That means f at any point on this curve, that is f at x1t x2t is equal to mu. Now we see that on the left of this equation we have a differentiable function of the variables x1 and x2, and these x1 x2 are now appearing as two functions of one single variable t. So by the chain rule of the composite functions of several variables, we get df dt is equal to del f del x1 dx1 dt or x1 dash t plus del f del x2 into x2 dash. As the function value f is constant on L mu, if we take derivative on this left hand side, we will get the value 0, and therefore we simply get 0 is equal to, this expression is dot product of the vectors grad f at any general point on this level curve and the direction of tangent at the parameter value t. In particular, we choose the value of t, say t equals to t naught, so that at t naught we get this point C on this level curve. So at this point C in particular we get grad f at C transpose the direction of tangent on the level curve at the point t naught is equal to 0. Hence grad f at C is perpendicular to the tangent vector at the point on the level curve L mu at the point C, and that is the result that we have stated over here. Now for functions of several variables, you will just have, instead of two components here, you will just have n many components. Here also you will have n many components. Accordingly, you will end up with n many components in the gradient and n many components in the direction of tangent. So just by writing more many number of variables, you will get the proof for this result for a general function of several variables. Now with the help of this denotation of gradient, I would like to mention a very special representation of the Hessian matrix. Note that if we write the function of partial derivative of the function f with respect to its jth variable by the notation say fj, we can notice that the Hessian matrix of the function f at the point C is given by the first row as the gradient of the function f1 at the point C its transpose. The second row is gradient of f2 at C its transpose, and the nth component is grad fn at C its transpose. You please tally with this expression of the Hessian matrix with the Hessian matrix that I have defined earlier in this lecture. Next, we will prove a result that directional derivative of a differentiable function of n variables is given by the dot product of the gradient and the direction along which we take the directional derivative. I will just give you a hint for proof of this result. You may please write the entire detail of this proof. Notice that if the function f is differentiable at C, then we have f of C plus t d hat is equal to fc plus the linear function LH, whose expression we have already identified by j equals to 1 to n del f del xj at C times hj, the jth component of this t d hat is given by t dj. If we are taking up this d hat is having components d1, d2 till dn plus some function alpha of t d hat, where d hat is a constant vector, so we can just simply take a function of just one variable t over here, where alpha t over t tends to 0 as t tends to 0. Now from this equation, we see that when t is not equal to 0, if we divide on both the sides by t, then we get 1 upon t f of c plus td hat minus fc is equal to this sum j is equal to 1 to n of del f del xj at c times dj plus alpha t divided by t. Now as t tends to 0, this right hand side is equal to just this expression, which is nothing but the dot product of grad f at c with the unit vector d hat, and therefore limit of this left hand side expression exists, and we all know this limit when exists is denoted by f dash c at d, which is the directional derivative of the function f at c. I will end up this lecture by mentioning a derivative expression for a function of one variable defined by the expression of a function of several variables. Let us suppose we are given a function of several variables and a point C in Rn. Let us also suppose that D is a direction in the n-dimensional Euclidean space. Now we consider a function of one variable t given by f of c plus tt. Then we notice that the derivative of the function phi at a general t is given by the derivative of the function f of the arguments here are given by c1 plus td1, c2 plus td2 till cn plus tdn, where c1, c2 till cn are the components of c and d1, d2 till dn are components of the direction d. Now here treating this expression as a function of t, this expression as a function of t, and this expression as a function of t, we employ the chain rule here, provided this function f is a differentiable function on the entire Rn space. By chain rule, this right hand side expression is given by del f del x1 dx1 dt plus del f del x2 dx2 dt plus so on till del f del xn dxn dt, where all these partial derivatives del f del x1 del f del x2 del f del xn is computed at this general point having components c1 plus td1, then c2 plus td2, and so on till cn plus tdn. Now this expression on the right is the dot product of the gradient of the function f at c plus td with the vector whose first component is this dx1 dt, which is d1, second component is dx2 dt, which is d2, and nth component is this dn, and therefore dot product with the given vector d. In particular, if we take t is equal to 0, we get phi dash 0 is equal to gradient of the function at C dot product with the direction D. Now I will end up this lecture by mentioning the hierarchy of partial derivatives, directional derivative and differentiability. To find this hierarchy, let us relook at the results that we have gone through so far. We have seen that if a function f is differentiable, then it has directional derivative at the concerned point C along every possible direction d hat. Next, we have seen that if a function f is differentiable at a point C, then all partial derivatives with respect to all the variables of the function do exist. So differentiability implies existence of directional derivative as well as existence of all the partial derivatives. We have also seen that if a function f is differentiable at a point C, then that function f must be continuous at that point C. We have seen over here that existence of directional derivative along any direction at a point C does not necessarily imply the continuity of the function f at C, and hence existence of directional derivative along all directions at C does not necessarily imply that the function f is differentiable, because had it been differentiable, it must have been continuous at the point C. Now from the definition of directional derivative, we see that in particular, if we choose the direction d hat in this definition as the jth unit vector in the standard basis of the n-dimensional Euclidean space Rn, then the directional derivative along that direction d hat is equal to limit t tends to 0 1 over t times this expression where this d hat is being replaced by the vector ej. This expression with d hat equals to ej gives us the partial derivative of the function f with respect to the variable xj at the point C. So existence of directional derivatives along all directions d hat implies existence of partial derivatives. Now accumulately all these observations now gives us the hierarchy of partial derivatives, directional derivatives and differentiability, which we neatly write as follows: that differentiability is the superior concept which implies existence of directional derivative, which we abbreviately write as dd, at the point C along all directions d hat belonging to Rn. Now in particular, you choose d hat to be the jth unit vector of the standard basis of Rn space. You will get that existence of directional derivatives along all d hats will imply existence of partial derivatives at C with respect to all the variables of the function f. Now here I would like to mention a sufficient condition under which existence of partial derivatives imply the differentiability of the function f at C. A sufficient condition is that if all the partial derivatives exist in some neighborhood of C and are all continuous, then the function f is differentiable at C. So if fxj is continuous in some open ball centering at C for all xj's j equals to 1 2 till n, then the function f is differentiable at C. I will neatly write out this statement. For a proof of the statement, you may please visit the book entitled Mathematical Analysis by Apostle. The result on the sufficient condition of differentiability states that, let us suppose we are given a function of several variables, say of n variables, and assume that one of the partial derivatives f(x)(j) exists at C and the remaining n minus 1 partial derivative functions do exist in some neighborhood of C and are continuous, then the function f must be differentiable at the point C. For a proof of this result, you may please visit the page number 357, the theorem 12.11 of the book entitled Mathematical Analysis by T.M. Apostol, which came out through Edition Wesley. You please look at the second edition of this book, which was published in the year of 1974. With this, I end up this lecture here. But before ending, let me give you a few questions to work out. The first question that I would like to give you is the following. Consider the function f x1 x2 is equal to x1 plus x2 when x1 x2 is equal to 0 and 1 when x1 x2 is not equals to 0. For this function, show that both the partial derivatives f(x1) and f(x2) do exist at the point 0, 0. However, for any direction, those are not along the x1 axis or x2 axis, the directional derivative of this function does not exist at 0, 0. For the second question, consider the function f x1 x2, which is given by x1 by modulus of x2 times under root of x1 square plus x2 square when x2 is not equal to 0 and 0 otherwise, so that this function f is not differentiable at the point 0, 0, but it has directional derivative at 0, 0 along any unit direction d hat in R2. The third question is that you consider this function that I have given in this question 2 and calculate gradient vector at 0, 0 and the directional derivative at 0, 0 for the direction 1 by root 2, 1 by root 2. After calculating this directional derivative value, you please check if this directional derivative value along the direction d hat, which is given by 1 by root 2, 1 by root 2, is equal to the dot product of the gradient vector and the direction d hat. You will find that they are not equal, and then I would like to ask you why they are not equal. The last question is that so that the function f x1 x2, which is given by x1 to the power 6 minus 2x2 to the power 4 divided by x1 square plus x2 square, when x1 square plus x2 square is not equal to 0 and 0 when x1 square plus x2 square is equal to 0. This function is differentiable at the point 0, 0. With this, I stop the lecture here and put my sincere thanks for your kind attention to listen this lecture. In the next lecture, we will consider to discuss Taylor's theorem for functions of several variables. Thank you all for all of your kind attention.